Hey everybody, it's Mr. Francis, and here's my quick review for Chapter 20. We're in nuclear chemistry now, and the first part of the chapter actually brings up an interesting aspect. Not all the elements in the periodic table we know are naturally made. One of the first artificially produced elements is that of technetium, and you can see the information here, and you can see, actually how it was produced. It was a bombardment reaction. It was, and this is kind of in the early years for that. If you've ever been exposed to technetium, this is what it looks like in the skeleton itself. So the first part of the chapter, we're going to focus on the reactions. In a chemical reaction, as we know, we always focus on balancing the atoms. We focus on, they talk about the electrons, the valence electrons being disturbed. In a nuclear reaction now, we've got to focus on both the number of protons and the number of neutrons and make sure that those are balanced in there. Because now in these nuclear reactions, we're actually going to see the formation of new elements, which is something that we hadn't talked about, that we've talked about, that doesn't occur when it comes to reactions. Nuclear reactions can fall under one of two categories, and you see the two here: radioactive decay, nuclear bombardment. And we're going to go through, I'll go off quickly the distinctions between both of these. But the aspect of radioactivity has actually been around over 100 years, and in some cases is actually found by accident. And you talk about here the work by Henri Becquerel and working with uranium plates and how he noted alpha rays, gamma rays, and beta rays. If the alpha rays seem somewhat familiar, excuse me, those are the same alpha rays that Ernest Rutherford used in his gold foil experiment. So there's three types of radiation that can be emitted, three types of radiation that Becquerel noted that can be emitted: alpha particles, beta, and gamma particles. And you can see the distinction between each of the three. Now, the nuclear equations, whether they are decay reactions or bombardment reactions, the key to these is this aspect here, that they are balanced in the mass number and the atomic number on both sides. And you can see that with the uranium here. Add up the atomic numbers down here, the mass numbers up here, and you can see they're balanced on both sides. That's going to be a key as you're looking at the equations in this chapter. Here are some of the particles that we'll see in the notation. And this is something, go back to this when you need to, if you can't remember off the top of your head what these involve. Okay. Again, more distinction in terms of the types of particles that we have. So here's this example. We're working with radium-226 and we go to radium-222. Okay, now thing to keep in mind, when it's written like this number here is your mass number. So you will have to go to the periodic table to find your atomic number. So for radium, that's 88. For radon, that's 86. And again, note that everything adds up. When we talk about decay reactions, the decay particles always going to be on the product side of the equation. As we'll see with bombardment reactions, they always end up on the reactant side. And again, the information in terms of balancing a nuclear reaction. And again, here's another example, this time with technetium-99. And here now we're trying to find what the mystery element is. Not mystery, but the new element that gets formed. And again, we add up the mass numbers, make sure they're constant on both sides. The atomic numbers, here it's 43. So we need to find something plus a -1 equals 43. Hey, that's 44. So we can look up element 44, which is ruthenium. And hey, there's there's the product nucleus, as they call it. Same thing with iodine-131. And again, look at how this is broken down, and they do the math to determine the elements for this. Interesting thing about the isotopes is they tend to be very stable. And the stability, I like this, the nuclear force. And you can see the definition there. So everything's very close together. Much like the arrangement of the electrons in the atom, within the nucleus of the atom, we have the same shells, and that's where the protons and electrons exist. And this is one of the great terms in nuclear chemistry, and that is a magic number. There is a magic number in terms of the combination of protons and neutrons that an isotope wants to reach. And if it reaches that combination, it's going to be stable. And again, here is, in this table, just the combinations of how many stable isotopes we're truly working with. This is a chart that details it. Everything in this area right here are going to be where our stable isotopes exist. And what you see in the darkened spots, those are each of the stable isotopes. What's also nice about this chart is it kind of tells you, hey, if my isotope falls under here, or here, or here, it's going to tell you what type of decay it's going to undergo so that it gets into this band of stability. And again, this is just kind of a breakdown of what we're going to see for the types of decay reactions that we have. There are 6 types of decay, and each one dictates the particle. So we go from alpha emission, beta emission, and again, note the particles that you're seeing in each of the equations. Positron emission, electron capture, gamma emission, and then also finally spontaneous fission. And we'll get more into fission later in this talk. And again, this is just going into, hey, this is the range that we can use to tell us, here's where we're going to see, here's the isotopes that we're going to see undergo what type of decay. And I like that this is table 20.2. And this will give you the conditions that will tell you this is the type of decay that you're going to see. So here's calcium-47. They ask us to predict what type of decay is it going to have. We'll look at the argument here. The atomic mass for carbon is 40.1, but we've got a mass number of 47. So that mass number is much larger than the normal mass for calcium. We go back to table 20.2. Hey, when those two are this, it's probably going to be this beta emission that comes out. And that's what we see. There is a decay series, and I do want you to, I'm not going to go too much into it, but what you can see is, hey, from uranium-238 working all the way down to lead-206, and lead-206 is one of those magic numbers. Here's the entire decay process that you would see. If decay reactions always involve, a particle being emitted, bombardment reactions, now that same particle is going to be hitting the target nucleus. And in doing that, that's what's going to form new elements. So Rutherford did this in his discovery of the proton. He took nitrogen-14, bombarded it with helium. He formed this oxygen-17. That was nice, but it's this proton, and it was that proton that was emitted. This is the reaction that Rutherford used to prove that protons exist in the nucleus. Likewise, Chadwick, who is credited with the discovery of the neutron, here's the equation that he used, the reaction he used to discover the neutron in the nucleus of the atom. Technetium that we saw at the beginning, that's the first radioactive element that was formed artificially. The first radioactive nucleus that was formed is this phosphorus-30. And you look at the discoverers here, 1933, and you look at the bombardment reaction and the decay reaction used for that. And again, in each of these reactions, do the math real quick with the atomic numbers on the bottom, the mass numbers at the top, and you'll see that balance. We do have some simple notation that you use for bombardment reactions. Instead of having to write everything out, in the parentheses, we're putting the particles. What's our bombardment particle? What's our emitted particle? And that's what you see here. Again, some symbols for that. And again, here's a couple of examples going in each direction for the reactions. What can we use for these bombardment reactions? What we call particle accelerator. And these can be very simple, like a cyclotron, which you see here in the makeup of the cyclotron here, or they can be actually pretty complex. And for a lot of the newer elements that are discovered, they have some pretty complex bombardment reactions that we have. If you've ever heard anything like the CERN reactor in Switzerland, that is used to produce some of these elements. The transuranium elements being very interesting. You can read through here in the discovery of all the elements past uranium and the discovery and where we found those. And again, you see with the reaction, you see how everything is balanced with this. With the transuranium elements, that did give us some work in the periodic table. And Glenn Seaborg is noted for that actinide series in the table itself. And there are figures in the book, some of the modern particle accelerators, whether it's in Batavia, Illinois, Oak Ridge, Tennessee, and also out in California with that. Some of these isotopes, again, these are radioactive. They emit energy, so we do have to take into account for that. We have instruments that we can use to measure the radiation that's given off. You've heard of a Geiger counter in their use, and this is the setup and the makeup of a Geiger counter with that. Same thing with a scintillation counter with that, and it just measures the exposure that you have. And there's measurements that we can make, what we call the Curie. And there is a safe amount of Curies that you can be exposed to on a daily basis or over a period of time. And that's something that's always measured for scientists going into this area. If you remember half-life from our discussions in kinetics, here it is again. We measure the half-life of these isotopes. And all we need to know is, hey, what's that rate constant? And if that's given to us, hey, we can do the measurement. For example, iodine-131. This is an isotope that's used in treatment of thyroid issues. And you can see it has a half-life of 8.07 days. So a 1 gram sample, medical officials, doctors, they can trace the effectiveness of the iodine on the thyroid every 8 days and see how it's been affected by exposure, because they know after every 8 days, they know how much iodine is still in the system. And again, with the half-life, as long as you have this value of K, you can do the calculation. And here you got, I think this is a technetium isotope. It has a half-life over 220,000 years. So that's something to keep in mind. Carbon-14, you've heard of radioactive dating, carbon-14 dating, same thing. So they go through the process here and how it's done, and and put that together. And likewise in medicine and the use of isotopes in medicine, very important. And you can see the different types of medical isotopes that are used and the treatment for that. If you've ever had a CAT scan, an MRI, this is a PET scan. It's what's called a positron emission tomography. And what you're seeing here is a normal brain. Here you are seeing a brain that's affected by schizophrenia. And you can see the damage to the brain because of the schizophrenia, the disease that's in there. The last part of the chapter focuses on fission and fusion. Those are two very easily confused terms, but there is a big difference. Fission involves heavy nuclei, and you'll see that in each of those. And again, the heavy nuclei splits into lighter nuclei, releases energy, and you see the fission reactions. They turn into actually chain reactions. Fusion now is the lighter nuclei. So there's our difference. Fission means heavy, fusion means light. And you see the reactions with that. If you've ever driven up by Burlington, Kansas, the Wolf Creek Nuclear Power Plant, that is a nuclear fission plant. And we actually, it controls the chain reactions for the fission reactions. It has the fuel rods, the control rods, and what each of those contain. But the schematic of it and what you see in the big dome is this. You've got the area with the fuel rods and the control rods, but the other important part of Wolf Creek is the lake, because that's the water source. That water gets converted to steam, that steam gets converted to electricity, and that's why you see the electrical lines leading out the way that you do. Fusion, again, light nuclei. There's only one successful place that can do this, because we've got to reach temperatures 100 million degrees Celsius. Very few reactors have been put together that can reach those temperatures, except for the sun. So, if you got any questions, send me an email. Keep up the good work and take care.